Bonsoir, mesdames et messieurs.
Good evening, ladies and gentlemen, and welcome to all of you. I'm very happy to see so many people back in the room for this second meeting with the sun. To start with this evening, I want to share with you a sentence by Galileo. The sun, with all its planets, takes the time of maturing grapes as if there was nothing more important to do. Our conference tonight is going to bring you to the center of the sun. And it is a great pleasure for me to introduce you Professor Alain Blondel, professor at the University in Geneva. And he's going to introduce our speaker for tonight, Professor Art McDonald.
Oh, ben c'est formidable parce que
This is great. I see here many faces that are very familiar because I see them regularly when I give my class about neutrinos at the School of Physics. Let's talk about Art McDonald. He's someone I like very much and I admire very much. He's a Canadian, English-speaking Canadian. He will therefore deliver his speech in English. He was born in New Scotland, in the eastern provinces of Canada, and he studied in Canada, but also went to Caltech in California for his PhD. Afterwards, he practiced research in a nuclear center in Chalk River in the northwestern part of Ottawa between 1970 and 1982. And then he became a professor at the University of Princeton, one of the most prestigious American universities. He left Princeton for a Canadian university called Queen's University in Kingston in the province of Ontario. And he became the spokesman of an experiment called Sudbury Neutrino Observatory, SNO. And SNO, as it's called, solved a problem that was encountered since 1968. We didn't understand what became of the neutrinos produced by the sun. Many experiments were done. Nothing was observed that was supposed to happen. And the Nobel Prize was awarded to the author of the experiment only later on, when Art McDonald and his team from the SNO finally understood what was happening. This is, amongst others, the story that Art McDonald is going to tell you tonight. He received many awards for his wonderful measurements. In particular, he was recently awarded with Yoji Totsuka from Keikei in Japan, the famous physics medal Benjamin Franklin. You all know Benjamin Franklin, who made experiments on storms and thunderstorms. So Art McDonald has been awarded with very prestigious prizes, but he is also a very simple person, very nice person. I'm sure that he'll answer all your questions, at least all the questions that will have been selected in the meantime, if you care to write them down on the piece of paper that have been distributed in the room. Without further ado, I shall give the floor to Art McDonald, but first of all, the question of knowing how the sun is working inside has been concerning mankind for a very long time. Many gods have been created to incarnate the sun, Ra, in Egypt, or with the Incas, everybody thought about Tintin and his adventures when we saw the poster announcing this series of conferences. But this is another story. We're going to try and learn what is happening at the center of the sun. Please welcome Art McDonald.
So they tell me if I start to speak, this mic will be now on. Okay, good, it works. It is a real pleasure for me to be here, a real pleasure for me to be introduced by Alain, a friend for many years. What I'm going to speak to you about today, as Alain has already said, is something that has puzzled people for many, many years. That is, what powers the sun? A question that actually led to a major controversy back in the 1800s between two very famous scientists, Charles Darwin, who was convinced that the Earth, and therefore the sun, must be at least 0.3 billion years in age, just by looking at simple things like the erosion in the Earth and how long it might take to have the valleys that have been created by that to have developed. But then there was a famous physicist who was Lord Kelvin. He did many very good things in thermodynamics and things of that nature. And in fact, the scale of absolute temperature, the Kelvin scale, is named after him. He did a simple calculation of how old the sun might be simply by saying, well, we know that chemical energy, the sort of thing you get from burning coal or oil or whatever, doesn't produce a lot of energy. The amount of energy you're talking about for the sun has to be produced by, for example, the energy that comes from the gravitational attraction that is happening as the mass of material in the sun is contracting and heating up. And he'd made a calculation of about 10 times lower than that. And that controversy went on for a long while. In fact, it's said that Darwin left specific numbers out of his later papers because he was worried about the question of this controversy. However, in the turn of the century, of course, Albert Einstein pointed out that matter can be converted into energy and vice versa, the famous E equals mc squared equation. And when in the 1920s, a particular scientist by the name of Aston did measurements with great accuracy of the mass of the hydrogen nucleus, the protons at the center of the hydrogen atom, and also of the helium atom, and in particular the fact that you now had four, in this case 2 protons and 2 neutrons making up the helium nucleus. He discovered that in fact if 4 protons were being converted into helium nucleus, for example, by some process of what you're now talking about as nuclear energy, which is known to be about 1 million times more substantial in its quantity than the sort of energy you get from chemistry. He had a plausible, Eddington at that time put forward a plausible idea for how the sun might be powered. In other words, nuclear power is fusion power. Fusing together of protons to produce helium is a credible source of energy. It took a while for the details of this to be worked out, for people to make measurements in the laboratory of exactly how this process may take place, in which 4 protons are converted to helium, giving out a substantial amount of energy, as you see in the equation at the bottom of the page here. And in fact, this gentleman, William Fowler, who actually was the head of the laboratory at Caltech, where I worked in the 1960s, worked out a system along with collaborators of how the sun is powered and also how other stars also obtain their power, because depending upon how massive they are, as we'll talk about later, there are different nuclear reactions that take place to provide that energy that powers the stars. In fact, Willie Fowler won the Nobel Prize for what's called nucleosynthesis, the synthesis of nuclei, or the synthesis of the elements, which is a subject we'll talk about in the course of this lecture, because we are able to study the sun in great detail these days. And there are models made of how the sun burns. And that's of tremendous intellectual interest. As you can see, it's been a topic for mankind for many, many years. It's also of potentially some practical interest, because you're talking about the fusion process. You're talking about nuclear fusion, which in projects like tokamak projects, the ITER project, for example, we are attempting to use that fusion energy as a way of obtaining energy here on Earth. And the process of what's happening in the core of the sun is the same as what is happening in the ITER reactor. The only difference is that in the case of the sun, it's being held in place by gravity. It's so hot that it would melt any container you tried to put it in. And in the ITER project, you are attempting to hold it in place by magnetic fields. And so understanding the sun has tremendous interest in terms of understanding our origins, but it also potentially provides a way of understanding what happens in a very, very hot plasma, as it's called, where nuclear reactions are taking place. The sort of reactions that are taking place in the sun that ultimately lead to this conversion of 4 protons into helium are shown here, as they are now thought to be described correctly by theory. In fact, this is what Bethe put forward in his description of how the sun burned. What you see in these reactions, for example, is a proton encountering another proton in this plasma and combining to form another form of hydrogen, which is called deuterium, which is essentially 2 protons, and a positive electron and something called a neutrino. And we'll come back to neutrinos in a moment, because that's going to be the secret to how one is able to study these reactions in great detail. And so this series of reactions goes on. Once you produce this deuterium, you can add another proton and produce helium-3, which is a nucleus that has 2 protons and a neutron. You can combine that with helium-4. Well, sorry, you first have to end up producing some helium-4, which you can through the combination of 2 helium, and so on. And so you end up with this series of reactions ultimately producing, at the end, the conversion of 4 protons into helium-4. Now, what I mentioned was the fact that each of these reactions, or many of them, actually show the emission of a neutrino. And so neutrino is not exactly something that you discuss over breakfast, although it's been suggested it's not a bad name for a cereal, perhaps, that you might have on your table. Neutrinos are not in common experience. We know about electrons. Those are what run in the wires and give us electricity. We know about protons and neutrons usually as being what goes in a nucleus of an atom, and the electron going around the outside to produce that atom where the chemical energy comes from the rearrangement of the electrons between the atoms. But neutrinos are very unique particles. Along with electrons and quarks, they are the basic building blocks that we think make up at least our universe of matter, the type of matter that we are formed from. We don't know how to subdivide them any further at this point. They actually come in 3 types. They're referred to as electron, mu, and tau neutrinos. And they are described in the Standard Model of Elementary Particles, the famous standard model that has been recently demonstrated so very, very completely here at the CERN accelerator, with the discovery of the Higgs particle, the final element in that model. Neutrinos are only interacting via what's called the weak interaction. They don't have an electric charge. They don't feel the strong interaction that holds protons and neutrons inside nuclei. And so they, as far as they're concerned, an atom that they encounter is like open space. They only stop if they hit the nucleus of the atom or the electron going around it head on. And so they can pass through the amount of lead that light would pass through in a year, which turns out to be about 1 million billion kilometers of lead, and only have a 50% chance of stopping. And so they can penetrate out from the core of the sun, where, as we see, they are produced in substantial numbers, and give us information, if we can detect them, from what's happening right in the core. Even though the sun is some of the densest material we know, it doesn't bother them. Neutrinos pass through it, they pass through the Earth, and they pass through us. In fact, you have many, many neutrinos passing through you right now, and maybe once in your lifetime, one atom in your body will be converted into another type of atom by the interaction of that neutrino. But they're very difficult to detect because of this weak interaction that they participate in. And so you have to have very big detectors, and you have to be ready when you see something that says, aha, a neutrino has just done something. If, for example, a neutrino were to strike your eyeball that one time in your lifetime, and if your eyeball happened to be closed, as many of them, I can't see very well, but many of them may already be closed in this auditorium, I'm not sure. I hope not. I'll try to keep them open for the rest of the talk. But you might see a little burst of light, and that's what we look for in our experiment, is a little burst of light. So this is kind of a summary of the sort of information we have for the basic building blocks these days. Quarks and electrons and neutrinos are the basic building blocks. There's three what we call generations, or three types of each of these. The up and down quarks, as we call them, are combined to make neutrons and protons, and neutrons and protons are the substance of the nuclei of which our atoms are made. So an atom is, in fact, electrons circling a nucleus containing protons and neutrons. There are also four forces. As you see, the things that carry the forces are represented on the right here. The electromagnetic force involves photons, the strong force involves what are referred to as gluons, and the weak interaction involves two carriers, Z and a W carrier. Neutrinos, as I say, feel only the weak force and gravity if they have energy or mass, and they're formed in a situation where one quark is transformed into another quark, or in those reactions in the sun where protons and neutrons are transformed between each other. In the sun, there's only one type of neutrino that can be produced, and that is the electron neutrino, but there is the potential, perhaps, for them to be transformed into one of the other two types, and that's going to be the subject of what we discuss today. The original Standard Model, in fact, did not have that as a possibility. It had neutrinos as a zero mass particle and not transforming from one type into another. In fact, if they do transform from one type into another, that's something that implies that they are not traveling at the speed of light, or they wouldn't have the ability in their rest frame, as it's called, in the way in which they are perceiving their movement to be taking place, to measure time if they're traveling right at the speed of light. And therefore, they cannot be doing that if they're performing the types of oscillatory transformations that are represented by their transformation into other types. And therefore, the implication is they must be traveling less than the speed of light, which in relativity implies they have a finite mass. And so all of that kind of goes together. The Standard Model says that's not something that we expect to be happening, but in fact, is that correct, is the question that was raised almost from the beginning of measurements of neutrinos from the sun. That is, can they transform from one type to another? Now, the initial measurements of neutrinos from the sun were carried out by the pioneer that Alain mentioned earlier, Ray Davis, who collected a large tank of cleaning fluid, put it in a mine underground in South Dakota, and starting in 1968 began detecting the atoms of argon that the chlorine in that detector were converted into by a neutrino striking them, as you see in the equation at the bottom here. He was able to develop apparatus that was capable of sensing a single atom of argon, and therefore had great sensitivity in being able to use large amounts of material in order to look for neutrinos. He had a collaborator who was a very, very good theorist. And I had a great time when I was at Caltech in the late 1960s because John Bacall was there as well in Willie Fowler's lab. Ray Davis was visiting, and the whole topic of whether they could measure neutrinos using chlorine was being explored by people making measurements of nuclear reactions involving chlorine and so on. It was an exciting time. And right from the beginning, John Bacall developed detailed models of how the sun burned using these reactions I showed you, which take place predominantly in the hot core. The sun is a very complex object. If you look particularly out in the surface areas of the sun, where you have magnetic fields affecting the sun substantially, you have convection currents, you have flow of material in the vicinity of the surface, you have what they call sunspots, you have solar flares. It's a very complex environment. Inside the sun, it's a much simpler environment. There's a core where these nuclear reactions are predominantly taking place, and the energy gets from the core out to the surface by radiation predominantly before it gets to this outer convective zone. And in fact, it takes about 100,000 years for a change in the core to have an influence on the surface in terms of, for example, the average temperature of the surface of the sun. And so Bacall actually set out to deal with a relatively straightforward model for the sun, but one that's fairly complete in the sense that he was making calculations starting with what the initial conditions of the sun were expected to be, which was a kind of a small region of excess density where the material that existed at the time the sun started to form began to feel the gravity and contract and eventually accelerate in its contraction to the point where there's a tremendous amount of energy has been deposited in the core region of the sun, heating it up, and eventually heating it up to the point where these nuclear reactions could take place. You have to get to a pretty high temperature before the nuclear reactions will take place because these are charged particles. The protons and so on in the nuclei are charged, and they repel each other by electricity, by electrostatic repulsion. And so you have to have them at high temperature and hence moving at high speed in order for them to go through those reactions we're talking about. But eventually you get to what amounts to ignition temperature for these nuclear reactions, and at that point you start developing tremendous amounts of energy. And these computer models started out with the types of materials that it was thought the sun may have started with, and they let the models evolve under all of these influences, the gravitational effects, the evolution of energy through the nuclear reactions, and they end up matching all the properties that we, or at least a number of the properties we know, the solar radius, its brightness, the fraction of elements heavier than helium on the surface, and in the process end up coming up with a pretty accurate prediction, it turns out, of all the other things that are listed here, with one exception, and that is the number of neutrinos that are emitted in the core of the sun. Because what Davis observed when he made his measurements over a number of years was that there were too few neutrinos compared to what was being calculated and matched the sun otherwise in great detail by about a factor of 3 or so. And so that set up what came to be known as the solar neutrino puzzle or solar neutrino problem. There were a number of attempts. His started in 1968 with the use of chlorine in the mine, as I mentioned. There was a large detector in Japan called Kamiokanda, which started in 1988 and was subsequently replaced by an even larger detector called Super Kamiokanda, which was using ordinary water to detect neutrinos. And then there were measurements that started in 1992 using the metal gallium and doing something very similar to what Davis was trying to do, of looking for whether there was a conversion of single atoms into other radioactive atoms. Now, these experiments had thresholds. In other words, they were studying neutrinos above this threshold. And what's shown here is actually the numbers of neutrinos produced as a function of how energetic the neutrinos are. And you can see they're really dominated. This is a logarithmic scale. And so the difference between here, oops, sorry, touched the wrong thing. The difference between here and here is 100,000 in its magnitude. So there's a big difference between the number of neutrinos produced by the PP reaction and the numbers produced by the boron-8 reaction, which Davis's experiment and the subsequent experiments, including the one I'm going to tell you about, which was the Sudbury Neutrino Observatory, or SNO experiment, that started in 2001. But what happened was, when these other measurements were made, it was found that the blue lines that you see here, which are the measurements of the numbers of neutrinos observed, when compared with the multicolored lines, they're colored according to which of the reactions combine to give you what you would expect in terms of the numbers to detect. In all cases, they were factors of 2 or 3 smaller in the experimental measurements than the theory calculated. So the situation was that either the theory, the solar models, were incorrect or incomplete, or perhaps there was something to be added to the standard model, such that neutrinos do not have a zero mass and are capable of transforming from one type into another. Because virtually all of these experiments were either exclusively or predominantly sensitive only to the type of neutrinos that are produced in the core of the sun. So in order to determine whether there was the right number of neutrinos being detected, you really had to go back and use the solar models to predict how many were being produced in the first place. So the experiment that we did uses a material called heavy water, which is actually, instead of H2O, it's D2O, where, as I told you before, deuterium is a form of hydrogen that has an extra neutron in the nucleus, along with the proton. And that makes it heavier, but because the chemical properties are determined by that single proton, it otherwise behaves just like hydrogen. And so when you have D2O, you actually find that, in fact, that's something that occurs in nature. And about 1 in 7,000 of all the molecules of water that you drink from your tap, in fact, are heavy water, heavier by that extra neutron in the deuterium. And we were able to obtain on loan from the Canadian government about $300 million worth of this heavy water for $1. And I think Geneva is a community that can appreciate that leverage. It's pretty good in any market, but if you can borrow $300 million for 10 years for $1, that's not too bad in terms of an economic situation. And we were able to borrow it because it was regarded by our government as a very fundamental measurement that could be made if this material were used. And with heavy water, it's possible not only to observe the type of neutrinos that are produced in the sun, those electron neutrinos, but also another reaction, which is the sum of all the neutrino types, all 3. So if the electron neutrino is changing into the other 2 types, you still detect it with this second reaction. So if you measure the electron neutrinos and you measure all 3, and they're the same, that means all 3 is just electron neutrinos. If, as was a possible solution, 2/3 of the electron neutrinos are turning into other types, you still measure the total number of neutrinos with this reaction that's sensitive to all neutrino types, and you measure only 1/3 of that with the reaction that's sensitive to electron neutrinos. And so we built an experiment that's a pretty weird thing. It's the size of a 10-story building. It's ultra clean. We took the type of standards that you apply when you're building, computer chips. Everyone wore clean clothing. Everybody took a shower after coming through the mine to get to this. It was 2 kilometers underground. It was designed to hold in the middle $300 million worth of heavy water in a gigantic bubble. It was 12 meters in diameter and 5 centimeters thick, about that thick. And engineering was done to be sure that you could do that safely. It is buoyed up by surrounding ordinary water, but in both cases, the heavy water and the ordinary water, there was high purification, so that there was very little radioactivity contained in the water. We looked in through this plexiglass or acrylic sphere with about 10,000 light sensors, each of them about that big. We estimated at one point for a lecture just like this that you could see a candle on the moon with that much light sensitivity. So it was really capable of observing even the faintest burst of light. We made sure that the liner was pure and clean and kept even radon gas from coming in from the surrounding rock, as you would like to do in your basement to keep radon out of your basement, because that's a radioactivity that would interfere. And ultimately, we were able to build this detector based on our measurements with approximately the amount of dust that you would pile on your thumbnail, about 1 gram of dust on the entire detector. And that was something that made it, it was essential to do that in order to do the experiment successfully. And the fundamental use of this heavy water that gave us that second measurement is what made the experiment possible. The reason why we had all this heavy water in Canada is that it is used in the Canadian style of nuclear reactor. It's used to scatter neutrons and slow them down, which you want to do in a nuclear reactor in order that they then produce the next reaction. They have to be slowed down first. But because compared to ordinary water, where there's that proton sitting there ready to grab another neutron, it doesn't grab neutrons particularly. It scatters them rather than grabbing them. And so you could save your neutrons for the next reaction. And so Canada had these reserves, and we were able to borrow them and make this experiment. So here's a little graphic of how we detected neutrinos from the sun. They stream out of the sun, and about once an hour, we detected a neutrino that had interacted in our detector. This shows you the sort of thing that was happening. This is 2 hydrogen and an oxygen, except if it's heavy water, it's an extra neutron and a proton. And there's first reaction here is one that is the type of reaction that is sensitive to all neutrino types. The second type, which is distinguishable in our experiment, is one that is only sensitive to the electron neutrinos. And so, as I said before, if you measure electron neutrinos and it's different from the sum of all neutrinos, you've demonstrated that they've changed from one type to the other, and you don't have to rely on the solar models in order to make the calculation. So we did this 2 kilometers underground in an active nickel mine. International Nickel was the company we worked with initially. It's now owned by Vale, a Brazilian company. It is 2 kilometers down. This is the ore, very rich ore in a place called Sudbury in Canada, which is noted as a nickel and copper producer. And it is at a site where you come down in a shaft, which is about 3 meters by 4 meters. All of the miners and we and all of the equipment we had to bring down to build this detector had to come down in this shaft. And the other side of the shaft is where the ore goes out. About 5,000 tons of ore a day goes out the other side of the shaft, and we had to coexist with the miners. So just to give you a feel for it, in Europe, it's the Eiffel Tower, and there are 6 Eiffel Towers down. In the United States, I would use the entire State Building. You may think I pronounced that wrong, but I have it on good authority. My 7-year-old son, when we were at Princeton, had a field trip to New York City and came back and told us that he was very impressed. He had seen the entire State Building. So it's about the same size as the Eiffel Tower. In any case, that's the depth, and we had to excavate a cavity about 10 stories high, which we did. It took us a couple of years to do that, actually. It's the biggest cavity that had ever been excavated at that depth. It looked like that as we were in the process of finalizing the construction. That's actually me here, and I had white hair already at that point. That's what it looked like if you look down from the top. This was the top of the structure that holds all of those light sensors looking in. And it was an exercise where we had to build first that piece of the detector, put the light sensors in it. We had a platform at the bottom which you could lift up and then bring it down again after you had suspended this from the steel cables at the top here. Start building the top of the acrylic sphere. You can see that this was a major engineering exercise or construction exercise, which took quite a while, but it was also something where you really had to do it accurately. The engineering of dealing with this soap bubble required that everything be perfectly spherical, and it looked like that as we were getting close to the end. There are all kinds of different difficulties we ran through in doing it, but ultimately we were able to produce it, and as I'll show you at the end, it's actually about to be used for yet another experiment of a fundamental nature. Here are pictures of what it looked like under construction. These are actually the light sensors that look in. This is the back of them, and we estimated about 70,000 showers altogether were taken by people during the construction process. We had systems for purifying the water very substantially. It was about 1 billion times more pure than tap water, which meant that you would have, with respect to the main contaminants, the radioactive contaminants that bothered us, uranium and thorium, you would have only 1 radioactive disintegration per day per ton of water. It was really very pure water. And we also measured that with great accuracy. And the reason we did that was that that reaction in which you are sensitive to all the neutrino types could also be induced by radioactivity. And so we had to be sure that it was taking place due to neutrinos from the sun and not due to radioactivity that we had left in the detector. And so by measuring the radioactivity in the water, which dominated our radioactive background, and by making sure that all of the other materials building the detector were very low in radioactivity, we were able to accomplish it. We had radioactivity levels that gave us effects of radioactivity producing that reaction, which were 10 times less than what was produced by the neutrinos from the sun. So if you had 1 per hour from the neutrinos from the sun, radioactivity only gave you 1 every 10 hours. And we measured that with some accuracy as well. As you can see, we actually had a visit from Stephen Hawking in 1998, an absolutely amazing man. I can't believe the spirit of that man. He not only continues to do science, his mind is still very active, he's also very adventuresome, and coming down 2 kilometers in a mine and going to see an experiment in something that he would be interested in doesn't faze him at all. We had him visit in 1998. In order to get him there, it wasn't going to be convenient with the wheelchair and everything to take a shower, so Inco at that time built a rail car, and he was vacuumed off before he went into the rail car, and he and his nurses and several of us traveled in the rail car with him, and then we took him out cleanly. Fascinating individual, asked all kinds of questions of our students, you know, picking out one word at a time on the computer on the front of his wheelchair. A very inspiring individual. We also had problems in building the detector. As I mentioned earlier, I'll just give you one that turned out to be a little bit humorous. The last phase of the experiment, in order to detect that reaction sensitive to all neutrino types, instead of looking for bursts of light, we actually put in an array, about 1 kilometer of neutron detectors that we put in. There's about 120 of them. They had to be put in one at a time using a little submarine, a remotely controlled submarine. And so if you're going to build a submarine, what color would you have? Inspired by the Beatles, you obviously would have something that looks like a yellow submarine like that. So we did it, and it wasn't quite exactly the right thing, because that darn yellow paint was, as it turned out, far too radioactive. We had to strip it all off, and so the submarine eventually became a prosaic green color. One other interesting aspect of it was that nobody under the age of 23 had any facility whatsoever in flying this submarine to try to put things into place. And that was much to the consternation of, for example, my good friend who was about 60 at the time and a level 2 ski instructor, could do everything else, but couldn't do that anywhere near as well as our graduate students could. So that is the sort of thing you deal with in a big project like this. So here are our results. And you remember we were measuring 2 types of reactions, one of which is very specific to electron neutrinos alone, the type produced in the sun, and the other which is sensitive to all neutrino types and might be expected to match the calculations of the solar models if, in fact, electron neutrinos are partially converting into other neutrino types. And in fact, that's just what we observed. This reaction, with substantial accuracy, it was an excellent agreement with the solar models. This measurement was about 1/3, exactly what Davis observed in his original experiments. And so the explanation, now without relying on solar models, was in fact that 2/3 of the neutrinos are changing from electron neutrinos to other types before they get to the Earth. And so it's a particle physics solution. Changes had to be made, or extensions had to be made to the standard model in particle physics in order to explain this. And the solar model was very accurate. So in addition to defining the fact that solar models work very well, we were able to do some very interesting particle physics. And there is now a theory which postulates that there are massive neutrinos and that oscillations can take place between the type that are produced and the type that you eventually detect as a result of this massive nature of neutrinos. And they've been verified in many ways. There was a very nice verification for muon neutrinos in that same Super Kamiokande experiment in Japan. In fact, prior to our measurement of the ones for electron neutrinos. And there have been confirmations with measurements with reactor neutrinos since then. So it now fits very, very well with those measurements, with accelerator measurements. For example, Alan is involved in a very sophisticated experiment in Japan called T2K that's providing very interesting final details on the models for how this works. And so we're able to take independent information and predict what we might expect in terms of how the neutrinos change from electron neutrinos to other types in transit from the sun. And I'm going to show you that in the next slide, along with our results and results from some of the original experiments and some results from a very nice new experiment called Borexino that's taking place in a major European underground laboratory in the Gran Sasso tunnel in Italy. And what you see is what the prediction is for, I've got to stop hitting the wrong button here. What you see is the prediction for the fraction of the electron neutrinos that survive as a function of energy. That's this gray band here. And then projected on that is where you would expect the data to show you a number of neutrinos detected, assuming that the solar model is correct. This is for the lowest energy neutrinos, the pp neutrinos. This is for neutrinos from a reaction involving beryllium-7. This is for another reaction involving protons. And this is for the highest energy neutrinos, the boron-8 neutrinos. And so what you see is that the solar models really predict very accurately when combined with what we now know about particle properties of neutrinos. And so we're really predicting how the sun burns, excuse me, how the sun burns with great accuracy. In fact, if you take out the neutrino physics and just ask, how do the fluxes or numbers of neutrinos observed compare in terms of the measurements over here with a couple of different solar models with slightly different starting points for the fraction of heavier elements in the sun. And what you find is that there really isn't a big variation in the solar models, and the experimental results are in the same, well, within accuracy, match very, very well what is predicted by the solar model, including a nice new measurement of the pp neutrinos directly by the Boraxino experiment. Now, I mentioned earlier that within this sort of accuracy, which in this case is about 10% or so, and in general can be a little bit better than that, what we're measuring with the neutrinos is the way the sun is burning at its core today. And it takes about 100,000 years for a change in that to have an influence on the surface of the sun. And so at this sort of 10% level, we're not expecting a substantial change in the way in which the sun is burning. In fact, we're expecting that it will be billions of years before there is any substantial change. Now, it turns out even small changes, as you'll hear on Thursday from Jerry, can have quite significant effects on the Earth, the sorts of things that happen on the surface of the sun. The solar, things related to the solar cycle, so-called, can have rather substantial effects on our climate and on other things. But in general, we're expecting the sun to evolve the way the models predict. And I'll come back to that in a moment. The other way in which solar models have been verified with great accuracy by measurements is by measurements of, if you like, the sun studied from seismology, studying by how it oscillates, stimulated by the sorts of things that are happening inside it. And what has been detected in particular are oscillations that show up in the oscillation of the surface of the sun that are due to acoustic waves, referred to as P waves, that are influenced by everything that's happening inside. And by analyzing that data in great detail, and the Gong experiment, and a scientist by the name of Sylvain Turcchiez is responsible for a lot of this. She's from Paris. The results show that the solar models work very well for the internal density of the sun that these measurements are sensitive to. So, as I said, one of the things that we have as an objective in studying the sun is to understand the elements that make us up. And this is a plot of the abundances of various elements that we find on Earth and in fact, in general in the solar system, meteorites and so on as well. And what you see is it's dominated by hydrogen and helium. This, again, is a logarithmic scale. And so there's a factor of 10 for every element here. And so between here and here is a difference of a billion times in terms of, for example, the amount of, let's say, niobium and the amount of hydrogen predominating. Now, the question is, how did all this occur? How did we end up with all of these things being generated? Well, it starts back in the Big Bang, or shortly after the Big Bang. And you heard a bit about the Big Bang last night. In general, if you measure all the stars that you see and measure how they're moving away from each other and from us, you find that roughly 14 billion years ago, they were all roughly in the same place. It's as though there was a major explosion at that time, and that is what has resulted in the evolution since then. Now, some of the atoms have been created back at that time. Predominantly hydrogen and helium were created shortly after the original Big Bang. Here's a graphic of of the way in which the universe is thought to have evolved these days. 13 billion or 14 billion years ago, there was a big explosion. There was then an inflation, which is a topic of major controversy these days, but there was a very strong expansion. And thereafter, the universe continued to cool. At about 10 to the minus 4 seconds, the quarks and the neutrinos and electrons and so on found themselves, after their creation by energy having been converted into matter and antimatter, equal amounts, back in the early universe, they found themselves in a situation where 3 quarks could come together to form protons. You then ended up cooling after about 100 seconds to the point where nuclei could start to form. After about 3 times 10 to the 5th years, you had atoms forming, and then they formed into stars and galaxies. And from this material, stars like our sun would be produced. And it turns out that going into great detail, which is what Fowler got the Nobel Prize for, of how this happens in different types of stars, and eventually when stars run out of their energy and collapse, producing what's referred to as a supernova, you produce those various elements that I showed, and by and large you can understand in great detail exactly how that comes about. In the sun itself, as the sun becomes more mature and as the hydrogen begins to run out, you end up with the generation of carbon, oxygen, and nitrogen. Even at its present stage, you can observe these effects if you have very sensitive experiments, and that's the subject of the next generation of experiments. For the SNO experiment, it's what we call SNO+, and the Boraxino experiment also has great sensitivity for doing this. The expectation of the models is that our sun will continue to evolve over about the next 8 billion years or so. It will become what's referred to as a red giant, a very large and lower luminosity, well, more energy coming out, but a kind of a reddish exterior, and eventually it will burn out, and then it will distribute its elements into the surrounding region. And some of the elements making up the sun probably came from a similar effect for other stars. For stars that are more massive than the sun, there's a whole progression of sequences that go through. Ultimately, they end up with a situation where you burn hydrogen first, then helium. Oh my, sorry. Hydrogen, then helium, and then all the various elements up the periodic table. And every time you run out of fuel, in one burning cycle, the sun contracts a bit more, gets a bit hotter, and the next thing starts getting burned. But when you get to iron, it turns out that if you fuse nuclei heavier than iron, you don't get energy coming out anymore, and so the star kind of peters out, and it collapses, producing either a black hole, if it's massive enough, or a neutron star, which is about as much as you can compress material to the point where the neutrons are so close together you can't compress it anymore. Now, these supernovae are remarkable events that we see all the time in other galaxies, where suddenly a star becomes very, very bright all of a sudden, usually within about 10 seconds or so. We've only directly detected neutrinos from supernova in our galaxy once. They're predicted only to occur in our galaxy about once every 30 to 100 years, but that was in 1987. And in fact, about a dozen neutrinos were observed. The energies of them, the time distribution was exactly according to the models that predict how supernova should occur, and also the models that predict how all of the elements beyond iron should be produced. And so we have a pretty good idea of how all the elements are produced, and that's what this table is. It's a table of the elements, and it's got a legend on it. You can see that small stars, that's like our sun, produce carbon, nitrogen, oxygen, neon, sulfur. But carbon, nitrogen, oxygen is pretty important for life. And so you really can say that understanding the sun is understanding the things of which we are made. The larger stars produce the heavier elements, predominantly up to iron, and then the brown ones here are produced in the supernova. And of course, there are a lot of elements that have been produced in very high energy accelerators, including CERN. So understanding how the sun burns is pretty important in terms of trying to understand where we came from. And so we're moving on. Our next experiment is a reuse of the snow experiment. We call it Snow Plus. Not much imagination there. It was about the time that The Matrix Reloaded was on the film, and one of our people suggested that maybe we should call it Snow Reloaded, because that's basically what this is. We're putting a material in place of the heavy water that gives off about 100 times as much light and enables us, we hope, to be able to observe those very low energy neutrinos that come from the CNO cycle I mentioned. In order to do that, we had to hold down this acrylic sphere because this liquid scintillator is lighter than the surrounding water, and so that was a major tour de force that has taken place, and there you see it as it is, or as it was about a month and a half ago, with the ropes. You can't see them very well with the lights on, but the ropes holding the central sphere. Right now, it's about half full of water again. And so sometime in the next year, we'll have some data with water and then replace it with liquid scintillator. The other thing that we can do with this experiment, and others as well, is study supernova. Because instead of getting a neutrino an hour or something like that, you'll suddenly get hundreds of neutrinos in about 10 seconds. And there are a number of experiments around the world, some of them are shown here, that can, in fact, observe these neutrinos. And what we've set up is a supernova early warning system, SNOOS, as it's called, which, when we had false alerts, used to wake me up in the middle of the night when I was the director of the SNOW project, and SNOW was a part of this. Snow Plus will be a part of it when we turn it on again. The idea is to very quickly confirm that several experiments have seen them, and to send out an alert to the astronomers. You can tell them roughly in the sky where the supernova is taking place, and they can shine their telescopes in that direction. It turns out that it takes a while for the light to develop in a supernova. Neutrinos are produced almost instantly, but by the time you get to the point where light is being significantly increased in a supernova, it can take up to several hours. So there's time for astronomers to go and look. After the SNOW project, we were able to expand our laboratory. We now have SNOW Lab, which is about 3 times the size of SNOW, with other areas here for new experiments, including a lot of measurements of dark matter, which I won't mention in detail today. SNOW has now become SNOW Plus, and there are many other experiments happening in the laboratory as well. You can see the type of cleanliness, the size of it, and you can also see that Stephen Hawking, about 5 months after he survived pneumonia back in 2012, I was talking to him about whether he wanted to visit again, and he said, sure, I'm better. In his terms, that means he can again try a trip 2 kilometers underground. And so there he is seeing the new laboratory surrounded by a group of our students, and still just the same remarkable man. At this point, he can only move his right cheek. That's the way he communicates. And it's just amazing to watch. We have one new experiment at SNOW Lab which actually uses that set of neutron detectors I mentioned before. It's called HALO, and it's also designed to study supernova. Along with, those are the 2 yellow things highlighted, along with a number of other experiments aimed predominantly at dark matter detection, where you also need to go underground and get away from radioactivity. So in conclusion, the whole idea of going underground to make measurements, as well as using satellites for things like the GONG experiment for helioseismology, has really enabled measurements of neutrinos, and by using them, we've been able to understand that the sun really, we understand it in great detail as to how it burns. And future measurements are going to make that even greater in terms of the accuracy. And so this also strongly supports the idea of how the elements in nature were produced starting with the Big Bang and working all the way through a whole series of complex processes that end up generating all of the elements of nature of which we're created. So it's been a fun exercise over the last 20 to 30 years to be able to do this, and I think we've added to knowledge of the sun in great detail, and it's very satisfying to have done that. Thank you very much.
Thank you very much. That was really a fantastic story to tell. On va prendre une petite pause de...
We're going to take a 5 to 10 minutes break. First of all, to collect all your questions, also to enable our panelists to come to the table, sit down and collect their thoughts in order to answer your questions. In the meantime, we're going to look at your questions. Thanks.
Donc, on a le plaisir d'accueillir.
So we are welcoming our speakers back, and many questions are coming on my desk. Mr. Braik, first of all. Oh, you got lost. Oh, well, too bad. Mr. Jerry Mieux, and of course Art McDonald are our guest tonight. This is the first time that I'm trying to sort out questions amongst those that have been asked by the audience. As a matter of fact, it's your questions, and it's wonderful because there are many, many different questions. I try to prioritize them. We'll probably have no time to answer all of them. Let's start with a few of them which I found fairly conducive to a good discussion. The first question, since this is the evening, is, I'm sure, directed towards one of our panelists and probably for Mr. McDonald.
During the day and the night, the distance between the sun and the detector may change because it goes around the Earth. Does that make more time for the transition? If any of you would like to answer, but I suppose Art is the best place for that.
Well, not the difference from the day to the night, but actually the yearly cycle is observable. After several years of statistics of accumulating data, that can be observed. There is, however, another process that leads these experiments to look very carefully at the difference between day and night, and that is that the neutrinos coming through the Earth, the electron neutrinos, excuse me, that survive can be reconverted to other neutrino types, and so you can have a change, in fact, between the numbers of neutrinos reaching the detector, depending upon whether or not they have gone through the Earth and had an opportunity to interact predominantly with the electrons in the dense core in the center of the Earth. And that is one of the things that these experiments look for, and you can determine properties of neutrinos by doing that. So it is this temporal information is something we look for, but not explicitly the difference in the numbers reaching us day and night that are due to the distance from the Earth to the Sun.
Okay. Any of you want to add to this? Okay, I come to another question which is still on particle physics and neutrinos. When and how do the electron-type neutrinos transform into the other two types? What's, where is that happening?
Okay, that actually involves a number of details that I really didn't have time in the talk to go into explicitly, but it's all part of the particle physics theory that I said is now really understood very well. It turns out that process of interacting with the electrons that electron neutrinos participate in, and I'll get a little bit technical for a moment, it turns out that the electron neutrinos can interact with electrons by exchanging either one of those W particles I showed you or a Z particle, whereas all three can interact with electrons by the exchange of a Z particle, electron neutrinos, mu neutrinos, or tau neutrinos. There is a process that takes place in the sun where the electron density is very large that essentially converts electron neutrinos into a pure mass 2 state. The way in which the transformation of neutrinos takes place is that you start off with an electron neutrino. It is made up of some combination of 3 different masses. As it travels, it can change that combination of masses and therefore look like one of the others in part when it gets to the point where it's detected. It's a quantum mechanical phenomenon which unfortunately I can't describe in any other way other than mentioning quantum mechanics. But it turns out that in the dense material in the sun, what starts as an electron neutrino ends up being essentially purely a mass 2 neutrino, and it stays that way until it comes to the Earth. It doesn't transform any further after coming out of the sun. And a mass 2 neutrino, as it happens when you make a measurement of it by our detector, it looks as though it's 1/3 electron neutrinos and 1/3 muon and 1/3 tau neutrinos. And that's why we get the results we get. So it's a sort of detail that I wasn't able to, for time, to go into in this lecture, but it's understood very well and matches the measurements that are made in all these other venues, the accelerators and reactors as well.
Oh, very good. Now I get a few questions that have to do with the how does the sun function? One of them is the following. Pourquoi le délai de...
Why is there this time lag of 100,000 years between what is happening at the core of the sun and what is happening at the surface?
Delay of 100,000 years between what happens in the center of the sun and what happens on the surface. So somebody else wants to answer?
Do you wish in French or English? Allons-y en français peut-être.
En français.
Well, maybe in French, yes. In 2 words, but maybe you can add something to my answer. When light is produced at the center of the sun, because there are thermodynamic reactions, a photon will come out of it. But this photon will interact just about like the tube or the underground at 6 o'clock in the evening. You're going to be quenched, and if you want to run in a tube car, you'll probably have to get into contact or collision with many other people. But then once you're free, you can go very far, and that's the case of the photon. 100,000 years within the core of the sun, and then once the photon is out of the sun, 8 minutes, it takes 8 minutes to go to the Earth. Yes, and let me add that when we discovered only 1/3 of neutrinos were being detected as compared to what was calculated, some people wondered whether we were not watching the death of the sun, because neutrinos are produced now, but light has been produced 100,000 years ago, and maybe that is a sign that the sun is decaying or dying. And some people were a bit worried, but maybe Art found a few dollars to launch a few experiments about that. Do not despair, because you see the past if you see the sun. If someone tells you how beautiful the sun is, tell them that's past, that's things past.
I got another question on how the sun functions, at least our relationship to the sun. Pourquoi la chaleur solaire?
Why is there no dissipation of the heat from the sun before reaching the Earth?
Heat from the sun. Why doesn't the heat from the sun dissipate in the cold interstellar medium before it arrives on Earth? One of you guys wants to answer?
Well, the light from the sun is affected primarily by interacting with other material in terms of, if we think of the light in terms of photons being produced, particles, in other words, of light being produced in the sun and heading towards the Earth, it's only if the photon interacts with some other material that it would be removed from the stream. And so there's a whole set of interactions that happen in the atmosphere of the Earth, and in fact that's what makes astronomy such a difficult subject in terms of trying to get a complete understanding of all the light coming from objects like the sun, because you have to look in windows, and otherwise the light is absorbed. If you, however, are dealing with the outer space, the material is so there is so very little material in interstellar space that there's very little opportunity for any one of those photons to strike anything else, and therefore there's very little absorption in that region.
Yes.
Yeah, maybe I could just add something to that. I'm not a solar physicist, I'm a climate scientist, but when I started working on the connections between the sun and the Earth's climate, I started talking to a lot of solar physicists, and I think Art gave a great example of how hard it is to measure almost anything having to do with the sun. He's looking at a very specific particle, a neutrino coming out of the sun, but it's almost as hard just to measure the total amount of energy that's coming out of the sun. And when they told me this, I said, how hard can it be? The sun's just up there, just point something at it and measure it. And they said, oh no, that's much more difficult than that, because like Art said, it's the sunlight that comes through the atmosphere, it gets altered in various ways, so you got to put an instrument on a satellite. And there's so much energy coming out of the sun that even just the edges of any instrument, you get these refraction effects, and they can make just tiny differences in the amount of energy you measure from the sun. So with each instrument that they launched, that they put on a satellite, they get a somewhat different measurement of the total amount of energy that comes out of the sun. And so they spend a lot of time trying to reconcile those measurements from different satellite instruments to get one time series, which we now have from the late 1970s, of direct measurements of the total amount of energy coming out of the sun. But even that's a difficult measurement to make. So almost everything with the sun, even though you'd think it's pretty straightforward, it's actually very complicated.
Juste un mot pour rassurer la personne.
Just one word to reassure the person who asked the question. There are stars 10 billion light years away from us, from which we receive light. We can see the sun and from here, but planets that are very far away could see it as well. Just like with a car, you can see the headlights much more bright when they are closer to you than when they are far away. But light also travels in a line, which also gives you an idea of the tremendous quantity of energy coming from the sun, because we can feel the heat on the Earth, and the fraction of the energy coming from the sun that we receive on Earth is nothing but the dimension of the Earth divided by the distance to the sun to the square. In other words, the sun radiates 1,000,000 times more energy than what we receive on the Earth. Well, that's lucky for us, otherwise we would be burnt.
And here, which have to do with the sun being active and generating explosions. So, que peuvent générer les
What can generate the many solar explosions that we can observe now?
Can they do those multiple solar explosions that we know nowadays?
J'hésiterais juste le temps que vous traduisiez une conséquence.
one consequence on Canada is the increase in the birth rates, because a solar explosion that took place a few years ago cut an electric power plant in Canada, and 9 months later there were many births. But now, more seriously, my colleagues will answer the question.
That is, however, regarded as a good thing in Canada. The effects of what's happening on the surface of the sun are very complex and not totally understood at this point, it must be said. And when you get into something that is as complex as the sorts of things that you saw in the figures I was showing of how the surface of the sun behaves, and in particular regions where there is relatively little illumination referred to as sunspots, regions where there are great protrusions and explosions, as you mentioned. People have been puzzling as to what causes this for many years. The current theory, I think, deals with substantial magnetic fields that are created in this region of the sun. The sun actually does rotate, and it rotates differently in different parts of the sun. And when you start moving electric charges, you can create magnetic fields in the process of doing this. And the sun, of course, is all electric charges. It's a plasma. And so these magnetic fields are themselves quite complex. And they create in the sun, in the solar regions, somewhat chaotic patterns, including these explosions. On the other hand, there are very regular patterns that are happening in the surface of the sun. In fact, you've probably heard of what's referred to as the solar cycle, which is most easily observable as the number of sunspots that occur as a function of each year. And there's a very well-defined roughly 11-year pattern that has been identified for hundreds and hundreds of years in that number, and it has substantial effects. In fact, it is thought on the climate of the Earth. Very difficult, again, to make that correlation between what's happening in the sun and what's happening in the Earth, because you have so many different things that could be causing effects in the Earth's atmosphere. But that's what we're going to hear about on Thursday night. And so whereas the sun's surface is very chaotic, there are things about it that are quite regular. And I don't think anybody has a really clean interpretation of exactly what's causing this 11-year cycle at this point. But it's a fascinating topic itself.
Yeah, so without giving away my entire talk for Thursday night, I think the interesting thing about sunspots is, like Art said, they've been observed for a long time, for many hundreds of years, going back into ancient China, like 400 BC. And so that's probably one of the longest aspects of the sun that has been observed, because these are, you can see them if you filter the light a little bit, or even through pinhole camera type things, or project them on a piece of paper. You can see them fairly readily, and you can actually count them. And so they've been counted for a number of years. And so that's one aspect that is probably the best known aspect of solar variability. But even the sunspot cycle, this 11-year, so you get a maximum number of sunspots about every 11 years, is not really understood what produces that. They went away for about 70 years in the 16 and 1700s. It's called the Maunder minimum. Coincided with something called the Little Ice Age, was when temperatures seemed to cool off over parts of the northern hemisphere. Solar physicists don't understand why that happened. And this is one of the things that is speculated on. What would happen if another Maunder minimum occurred starting next year, for example? We would not know it was going to happen beforehand. We don't have good predictive models of the sunspot cycle. And so these are all these things that actually I learned from my solar physics colleagues, of all the things they don't know, and they're studying. They have models, and Art mentioned that this rotation of the sun, this dynamo, they kind of view it as a dynamo, and they have solar dynamo models which they try to predict the sunspot cycles. But that's based on a lot of things they're inferring, and Art gave this great example of how a model was actually constructed based on inferences of what they thought was happening, which then were later verified by his measurements, which is a great thing that actually happens a lot of times in science, where you come up with a theoretical model and then measurements that are made later either confirm or you have to go back to the drawing board with your model. So there's still a lot we don't know about the sun, and we're learning more about how what we have observed could affect Earth's climate in various ways, but you'll hear more about that Thursday night.
Juste une petite remarque.
Just one further word. At the time when solar spots disappeared, the Sun King Louis XIV didn't accept the competition. Well,
associate the authority of the kings or presidents to such activity. Right, now we're going back to the neutrinos. There's a very fundamental question, and I bring it forward because I'm sure it won't come forward. It hasn't come forward yesterday, or it won't come forward on Thursday. Any estimate of the neutrino mass? We'll be talking about mass all night, and you never told us what is the estimate of the neutrino mass.
You're going to allow me to answer? You are perfectly capable of answering yourself.
Yeah, but I'm not here to answer questions.
All right, I'll give it a try. It turns out that what we measure in the observation of neutrinos turning into other types of neutrinos is the differences in mass between various neutrino types. And so we measure the difference between two of the masses, 2 and 3 as they're prosaically labeled, as being on the order of 0.04 electron volts. Now, we'll put that in perspective. An electron is about 500,000 electron volts. And so it's about, well, it's a substantially smaller fraction of electron mass. And so neutrinos are much lighter in terms of the difference in their mass than even the electron. And the difference between 1 and 2 is about 1/10 that figure that I just mentioned. Now, I'm talking only about the differences in mass. That implies that the neutrino mass cannot be smaller, or at least one of the neutrinos' masses cannot be smaller than that 0.04 electron volts I mentioned. But the sum of the neutrino masses, or the absolute magnitude of any of the neutrino masses, is not known as yet. We only have a limit. One of the measurements that is made here on Earth that's best is a limit made by looking at the effects on a radioactive decay of an atom called tritium. And its limit is about 2 electron volts compared to the 500,000 electron volts for an electron, and the 0.04 in the difference. It turns out that the models for how the universe has evolved, the cosmology, are remarkably sensitive to things like how the how slowly the neutrinos were moving when they interact with material when galaxies are forming, large-scale structure, as they call it, in the universe, how that's being formed. And there are limits on the order of an electron volt or so, simply from measurements of the cosmic microwave background and other astronomical measurements that are quite consistent with what's happening in terms of direct measurement. There is an experiment that's about to start within the next year or so in Karlsruhe, Germany, called the Katrin experiment, which is expected to improve the accuracy on the absolute mass by about a factor of 10. So as of right now, we can't really say that it's any less than about 1 or 2 electron volts, and therefore substantially smaller than an electron.
Yeah, I should add that, je vais quand même ajouter une chose, c'est que
I'd just like to add something. The neutrino masses in terms of energy correspond atomic energies, the various energies that are at the level of an atom. It's far smaller than nuclear energy. I mean, it's very surprising. It's very small indeed, surprisingly small, and that's one of the mysteries of particle physics today is to understand how come it's such a small mass. I mean, perhaps it's a pointer that the other things happening at other energy levels, or perhaps there are other reasons for this altogether. Theory is not very useful for neutrinos. Theoreticians are always wrong when it comes to neutrinos. We know this every time we've been looking at these beasties. We always have to refer back to what's been seen in experiments. This brings us more or less to the end of our time, but I still have one final question. Earlier on we were talking about solar explosions and the magnetic effects of the sun. And here we have a question which is as follows.
Between the sun and the magnetic poles on the Earth. I think it's a little bit different from the other questions. Do you have an answer to that? Art?
Well, I think what must be being referred to is the way in which the magnetic field of the Earth can actually be affected by solar wind, for example.
Right. Donc, je répète la question en français. Quelle est la relation?
I repeat it in French. What's the relationship between the sun and the magnetic poles of the Earth?
Donc, simplement, sur la Terre,
Well, on the Earth, there's a differentiation which has taken place. When the Earth was very hot, the heavy elements fell to the center. That's why we have iron and nickel at the core. And there's a mantle and the cross on which we're walking. So the iron and the nickel that are going around gives us magnetic field. So there's a sort of shield, and the sun, which is producing neutrinos and cosmic rays and charged particles. If they didn't have this magnetic field, we would be totally irradiated. So thanks to this magnetic field, the shield has been created. It looks sort of round at the front, and then there's a long tail. But a magnetic field, there are a few bumps here and there, and there's an Achilles heel on the North Pole and the South Pole. The particles can penetrate, and that's why we have these fantastic aurorae borealis. They're coming in through the Achilles heel. So they're not created by the sun, they exist on the Earth. It's a very serious problem that I'm not particularly involved in, but my colleagues haven't found out. Sometimes an inversion between the poles, what happens is no magnetic field, no shield, and the sun interacts and protects us. So two different things, and the sun has nothing to do with the creation of those magnetic poles, but we are protected. I mean, it's far more complicated in detail, but it's more or less easy to understand.
Into this.
The other aspect of how the sun affects things, and you often hear of effects on the Earth of, quotes, magnetic storms on the sun, is that there's a stream of particles that are emitted by the sun. Their energies are on the order of, in these units of electron volts, 10 kilo electron volts, or 50th of the energy, the mass of an electron. But there are very large numbers of them, and they stream towards the Earth, and they are deflected by the magnetic fields that Andre was telling us about. But they can also, there are so many of them, and they are charged particles, protons, electrons, and so on, that they can actually affect the magnetic fields on the Earth. They can actually move your compass, if you like, in terms of the effects in the Earth. And they can also create currents. You know, when you ground something, so-called, an electric circuit in the Earth, you're attaching it to the Earth, and you're depending on currents flowing through the Earth to enable the electrons to flow back and complete the path in your electric circuits. And when you have additional currents flowing as a result of this disruption by the solar wind, you can have effects such as increases in the birth rate in Canada. So they are substantial effects on Earth, and they are a valid reason for attempting to understand the sun in much more detail.
Juste une brève remarque, vous savez que pour les voyages...
You know that for interplanetary travel, if you want to go to Mars, there's a problem. I mean, if you go along to the moon, we can sort of rig it so that he avoids these storms. But if we go to Mars, then there are going to be these storms, and it's very difficult to protect oneself. You need very thick walls of concrete or a sort of lead sarcophagus that would keep the astronomers inside. So it's very dangerous, but on Earth we are protected by the shield. Phew!
Bon, ben ça s'est terminé tout seul. Merci beaucoup.
Well, I think we've come to an end. Thank you very much. Thank you to our speakers, and enjoy the rest of your evening.